let's start today's session. I've also started the recording. Great. So, because of your recordings, I think yesterday we survived. Okay, I'm just hoping that today it's mysteriously exiting, and even the webinar people they have no clue why is it happening. Okay, so because of your recordings, at least we have something. At least we have something. Okay, great. So let's start from where we left in the last session. So do you have any questions before we move? Okay, so let me turn off all the notifications so that I don't get disturbed. All right, so do you have any questions before we start?
No.
Okay, okay. So if there is no background noise, and you can keep yourself unmuted till the point of the people sign in. Okay, so all right. So we talked about many things about general data analytics. It's very important to understand normal analytics before we jump into the actual analytics. So we have so far talked about general big data architectures. We talked about various tools. We even talked about Python and we even talked about Spark. So we have talked about various tools, including R. We have talked about all these tools in order to understand the data analytics and big data analytics. Now, yesterday we started with our normal uh, detailed discussion on data analytics. Although all of these topics in itself are very huge, but we are trying to make it simplified and trying to go ahead quickly, okay, so that we just focus on the our main agenda, that is how do you analyze the data and how do you reach to certain conclusions or certain outputs. And so for that we realize that we need to sometimes we need to gather data, and in case of gathering data there are you have to design an experiment, and then in experiment you have various kinds of terminology which you use, and then there is sampling. We instead of sending the survey to all the candidates, we generally send the survey to a small sample of the population. Okay, and once you get the survey results, how to visualize the data? How do you visualize the data? So one is like using scatter plots. Scatter plots are like this. In the scatter plots, the conclusions you generally draw is whether the correlation between two variables is positive, negative, linear, curved, strong or loose or weak, and are there some very huge different data points called outliers. So you can see that these are outliers in our previous example. Okay. Now, next we talked about the technique to analyze data is convert them into bins, as in convert them into ranges. Okay. So for example, instead of plotting a scatter plot, we are converting them into buckets and then counting how many people are there in that bucket. Here, for each 10 years, we have created buckets, and then we are plotting the buckets against the number of people. Remember, on the y-axis, it's number of people. And based on that, we are reaching to conclusion on what kind of data is it. Okay? So in that, you have left skewed, right skewed, symmetric, and then you have unimodal, bimodal, uniform, multimodal. Okay. And sometimes examples of unimodal we talked about is the usual in class in a class. If you are trying to plot number of students against mm, the range of marks, then you will see you will see a plot like this. But if you try to plot the age as in the how old are people in a college, that range on x-axis, and on y-axis, this vertical axis, we are trying to plot, we are trying to put number of people in that age group. X-axis is age group, y-axis is number of people in that age group. So you will find out that there are two nodes, because one, you'll find that maximum density of people is either between say 2 to 4, or 0 to 4, or the maximum age might be from 6 to 10. Sorry, not 6 to 10. Sorry, this is height actually. On x-axis, it is the height of the students. Okay, height, on x-axis it is the height, and on y-axis it's the number of people in that particular height range. Height or age, you will always get two two models. All right. So then we talked about dot plots. Okay. So dot plots generally become overcrowded very soon. They become overcrowded very, very quickly. So, I mean, there's nothing new about dot plot. Dot plot is basically plotting like a scatter plot, just that instead of just putting dot here, we are drawing a vertical line. And dot plots are generally having number of people in the y-axis. Okay, so the difference between a dot plot and a histogram is, in case of histogram, on x-axis it's the range, it's the bucket. In case of dot plot, it's generally not the bucket. Instead, it's the particular number, and that's why it becomes quite populated very quickly. All right. So the other notation we talked about is box. Box means number of 50%. Okay, middle 50% people. Okay, that 50% people, and along with the median, if you draw, okay, such that 25% people are on the left hand side of the box and 25% of the people are on the right hand side of the box, and then if you draw the middle box, okay, that is the box, we call it, it's called a box representation. Okay, so the box generally tells you the skewness of a chart. You will see in the next diagram. So in this diagram, the generally this box is towards the nodal point. The median is towards the nodal point as well as the box. So it generally shows, this box generally shows the which side is your population, which side is, so if on the right left hand side you see, if there are left hand side there are only few people, that means the left hand side will be bigger. Why? Because we are saying this big line contain 50% of the people. Okay, 50% people are on this big line. Okay, and all right, so the box will be towards the side where more people are there. If if more people are towards the left hand side, box will be towards that, because towards that side the number of people will be too high, and therefore the 25% will finish quickly here, and 25% will take so much time, while this section will be highest dense. Okay, so that's why the box generally represents the left or right skewness easily. Okay, you can see the relationship between the two, three. All right. The other way of representing the data was using the heat map. So most of the things which we have talked so far, histogram and the box plot, both and the heat map, all three of them generally represent data in the summary format, because there are many cases you cannot really visualize data without summarizing. Okay, so if let's imagine that your website has got millions of viewers per day, and you want to see which portion of the website you are clicking mainly, which portion of the website gets clicked very quickly. So if somebody tells you that okay, on these coordinates, these coordinates, somebody gives you an Excel sheet showing you from this coordinate got these many clicks, that coordinate got that many clicks, and a big sheet. It wouldn't make any sense to you. Okay, it wouldn't make any sense to you unless you present it on the real thing and mark it with the heat map. So you can see here, most of the users see the left top first, they go towards right, then come down, and then this. So based on this map, you can clearly see what is the user behavior. Most of the users are towards this side of the page, towards this side of the page. That is why if you search for something, let's say test, okay, if you search for something like test, users will generally see this area. Users will generally see this area, will skip rest of the area. Okay, that's why it's very important to get yourself listed on the this side. Okay, so these are the, and similarly, while creating a website, you should keep you should keep your important stuff in this particular section of the page. All right. So these are the insights related to your page. Also, like for example, when we launched our No Big Data website, we had kept in here. So I'll try to show you. Okay, I'll try to show you if I can show you. Inspect. Let let me try to show you. All right. So all right. So you can see here heat maps. All right. This is our website's heat maps. So if you go to our home page, so it's loading our website. Okay, so you can see that lots of people actually click on these dots on the website, and otherwise, our links are fairly distributed. So people are not really too much clicking here. Okay, so and similarly, if you go back to, so you can see that, so lots of people are clicking on these icons, which is very counter, as opposed to our theory that people will click here or there. Okay, and also see in about there are so many people clicking here, and some people are trying to log in here. Okay, and so, for example, there are no clicks on this point, there are no clicks on this point, and so on. Okay, so do you see that? And similarly, if you go back a bit, let's say this particular page, all right? So I'll try to show you some heat map examples. Okay, so on this page, you will see lots of people actually click on training online. You see that? And then there are people who are clicking here, here, and people clicking here. What are the prerequisites? Kind of. So you can see that we are able to easily visualize the things using the using the I mean using the heat map. So this is an example of a real life heat map. All right. So that was an example of heat map. So coming back to the point, so this way, heat map is a great way to visualize the complex data, and helps you in number of ways. All right, and we also talked about yesterday measures of center, mean, median, and mode. Mode is most frequent one, mean is average, median is the middle value. Okay, middle value as in order things by their numbers and then find out the middle value. Then we try to plot them in on a graph. So here you can see that measures of the centers. All right. So measures of the center is the if you see median is a better measure of center everywhere. Okay, median is a better measure of center, and generally median is towards the nodal. If you have a normal curve, this the node, the more what do you call modal, the peak. Okay, so the median is generally towards the peak. And then we talked about standard deviation yesterday. In case of standard deviation, what you do is, Mehdi, I'm making you the panelist. All right. All right. Hi, Mehdi. So when you do the measures of spread, the measures of spread is how much data. Okay, let me go back a bit. Let me go back a bit. All right. So I had a nice diagram somewhere. All right, here. So here is the line. You see the line here? Okay. No, that's not a good example. I'll go with some other example. All right. Yeah. So we talked about standard deviation. Standard deviation is a measurement of spread. How 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 much our data is spread. If our data is spread too much, then our standard deviation will be bigger. If our data is not spread too much, then our data will be smaller. Okay. So, all right. So you can say that. Let me try to ask you a few questions. Okay. Let's say there are two. Let's say there are two. Okay. Let's call the left hand side as A and left hand B, right hand side as B. Okay, now let me try to draw a histogram. Okay, there is one histogram which looks like this. Okay, histogram as in here there are ranges. Okay, there are, you know, you can think of them like this. All right, and then you can think of these like this, and you can think of this really high, and you can also draw it like you can see that. So this is the histogram, and then let's imagine that there is another histogram. Sorry. Okay, let me. Okay, let me try to draw another histogram. Let's say the histogram goes like this. Okay, meaning a number of people on this 1, 2, 3, 4, 5, 6, 7, and then number of people here 0, 1, 2, 3, 4, 5, 6, and so on, say 7. Now this shows that there are only small number of people at 0, little bigger number at 1, little bit bigger number at 2, and then it starts decreasing towards 7. Again, here this is like this. Okay, so let's say that the average of these values would be somewhere here. Let's say this is the average, and this is the average. Okay, average means find out. So these are number of peoples. Okay, on the y-axis, people who got 0 marks is this, or people who have height 0 is there. people height who have height 1 did this, and so on. Okay, so here we are computing the average height. How do you compute average height? This into this divided by total number of people. Okay, so find out the sum of all the people's heights and then divide by total number of people. Now in this you can see that the so here there are some people, here there are some people. Now my question is standard deviation. Okay, so let me try to write the question. Which Who has more standard deviation, A or B? Yes, anyone? So you have this from the visuals of it, and you have this. So do you think the values in case of A are far away from the median as compared to the values in B? Yes. What do you say, Mehdi? Out of A and B, who has more standard deviation? So there are only few values which are far away from the average value, while this side there are more values which are far away from the average. So standard deviation is measurement of spread, as in how badly your graph is spread out. Okay. So which one has got more spread, A or B? So here, um, are there more values far away from the median, or here there are more values far away from the median, as a median, sorry, average? So this is a point where we have average. So are there more values towards, okay, I think it's my diagram which is causing a little bit trouble. So probably I'll take some example with little more concrete data. Okay, so let's talk about a simple problem. Like we'll just take 3 4 problems. Okay, 3 4 data points. Let's say in a class, of 30 people, there are total people called 30. Okay, 10 people got 10 marks. Okay, or let's say 10 people got 5 marks out of 100. Maximum marks is, say, max marks is how much? Say 50 marks. Okay, so 10 people got 5 marks, while uh, the okay, so let's just call one got 5 marks, two got 5 marks, okay, three got 5 marks, and or let me, can I decrease this number to something like 10? So let's say 1 and 2 got 5 marks each, while 3, 4, 5, and 6, they all got 25 marks. Okay, and then 7 got say 40 marks, and 8 got 40. So sorry, let me just put it say 30, and then this also got say 35, and ninth one got 40, and 10th one got 50. Okay, So this is our these are our data points. Okay, so all right, let's try to plot it. Okay, and the easiest way to plot, how did we plot? Okay, so maximax is this, maximax is 50, and let's say this is our a equals to this, these are our marks in the class. Okay, now let's say there is another class called B, which is a very strange exam in which the exam is very random. It has many random questions where everybody can answer a fair amount of questions. So let's say first person got 10 marks, second person also got 10 marks, third person got 20 marks, and or let's say third person got 15, fourth person got 15, and then okay, so next person got 20, next person got 50, 25, next person got 30, and so, and let's say next person got 35. How many people are there now? So 3 plus 3, 6, and now we have space for two more people. Okay, so let's say these are the two classes. Now, what do you see in these two classes? In here, lots of people are there near 25 marks and 35 marks, while in here, the number of people are averaged across the ranges. So out of, so do you see the difference? In case of A, you have more people towards the same number of marks, while uh, in case of B, the number of people is averaged out. Let's try to plot it. Okay, let's try to plot it. Let me start our studio. All right. So now you will be able to tell me the right way of. So let's say this. So take a closer look at. We have to zoom our plot sometime. It goes out of the. Yeah. So take a closer look at this. Okay. So you can see that the if you try to draw it, or because there are no person near 10. Let me just put it. Let's say one person is 10. All right. So let me just put it 30 and one is 40. Or let me just put it 40. Okay. So this is the data we have, and you can see that I'm trying to plot the histogram. Histogram shows us on y-axis it is not showing us marks. On y-axis it is showing how many people are there for this range, as in from 20 to 30, how many people are there? It's saying showing that from 20 to 30 there are 6 people. Okay, and similar is the case with okay. Now let's try to plot the second one. All right, let's try to plot the second one. I say histogram of B. Okay, now let's have a look. So you can see that most of the people are actually, this is not right. Let me try to make it a little more what I was planning. 0, 5, okay, 10, 15, and 25, 3 plus 3. Yeah, this is better. Okay, so now you can see the total number of people are higher in this, but people are spread across. So out of this histogram, okay, out of this histogram, okay, and another histogram, let's say we are talking about, where is my A? Okay, this is another histogram. So let me show it in another viewer, side by side. Okay, or we can just show it here. Can we show it here? Yeah. Can I? Yeah. So I think this will be clearer to you now. All right. So we have histogram and we have previous histogram. Histogram of A and B. Now out of these two, which one has got more standard deviation? Sahib, A and B. All right. Do you think values are varying more in A as compared to B? So in case of A, there are six values between 20 to 30, while the data is more sparse, as in it's spread across in B. So deviation from the average is more in A or more in B. Are people more deviant in case of A or in case of B? Right? So standard deviation of B should be more than standard deviation in A. Right? If people are varying away from average very high, let's take a country like India, where or let's take any country, you will find that the there are lots of people who are doing who have different or let's just count the number of times various digits occur when you throw a dice. Okay, it'll be equal. So it'll be equal, and therefore, since there is not much of a deviation, so here it's showing that there are equal number of people who are getting 0 marks, equal number of people, I mean, almost similar number of people there are here, but here people are very close to, uh, uh, there are maximum number of people at a certain point. Okay, so that is why if you try to see standard deviation of A, standard deviation of A and standard deviation of B. You see, people in the dataset B are more deviant as compared to the first one. Okay, I should have taken a more stronger example. So let's say there are one person at 15, other person at 20, and here other person at 35, and here other person at 40. Okay, so if we have this kind of diagram, and while in this we have 0, 5, 10, 15, 20, 25, 30, and so on, then the deviation will be still higher. Okay, so all I'm trying to say is that just by looking at the graph, sometimes you can guess the deviation. Okay, now if you compute the deviation of A and B, now there is drastic difference. Okay, so you can see now this is our histogram, which looks like a normal graph like this. Okay, and the histogram of B is this, where the values are spread across. Okay, therefore the deviation in case of B is very high. There are lots of people far away from the common behavior, and therefore the B in B there is lot of variance, or lot of deviation from the average behavior. Good. Was I able to conceptually explain what do we mean by spread? Mehdi and Anusha and Sahib. All right. So So this standard deviation is nothing but you first find the average, and then we find out how far are the values from the average by subtracting and then squaring. We square so that the negative becomes positive, and the impact of the difference is zoomed out. As zoomed out as in is squared, as in more difference, higher the value. Okay, so to give it more impact, increasing. Okay, so increase of larger deviation is more than the smaller ones. Okay, so that the weightage of higher deviation is still higher. That's why we square it out, and we took a couple of examples yesterday when we talked about variability and veracity. Okay, one is more variable, as in here there are more diverse. All right, we talked about this part. All right, so we earlier we talked about the interquartile IQR, which is range of 50% of the data. Okay, so that's very important part, and we say that we first find out here we find out where are the first 25% people, then next 50% people, and then so we find out the point at which 25% ends and point at which 75% ends, and the delta between the two is our IQR, Q3 minus Q1. All right, so that's how you compute the interquartile IQR. IQR is the representation of the average 50% people in your class. Average 50% of the people in your class. We are removing the losers and we are removing the excellent people. We are saying the middle 50% people. Okay? So in a graph like this, if we have a graph like this, okay, we have a graph like this. So how many people are there here? There are three people, right? And total number of people are 3 plus 2 plus 2 plus 2 plus 1, right? Total number 10 people, okay? So we are saying remove top 25% people, which is 2.5, approximately this, okay? And we are saying that remove the lowest 25% people, which is remove the 2.5 people, as in remove this plus this. Okay, so we get these many students, these many students in our class. Okay, which is 2 plus 2, which is 4 students. We removed 6. Now, so they start at what marks? They start at 10 and end at 30. So this is our IQR. So when we plot the box, this will be 10 and this will be 30. And then the median will be generally inside it. Okay, so this is our IQR. Is IQR clear to everyone? Good, good. And Anusha, was I able to explain what do we mean by IQR and the standard deviation?
Can you repeat the IQ?
Uh, what? It's okay, you can unmute if you're not.
R.
Yeah, interquartile range.
Can you explain it again, this slide?
Okay, okay. So IQR generally means remove. So we pick up the average 50% people from the crowd. Okay. So let's say, how should I divide again? Let's say, how many? What does mean by 25? Let's say we have 12 people in our class. Okay. Sorry. So let's say we have some people at 45 and some people at 3. Okay. So this is our class. First one has got, so we took the marks from our class. There was a class in which there was an exam. In this class, there were total number of students was 12. Okay. So let me change this. Total students was 12. Okay. And maximum marks was 15. So we gathered their answer sheets and taken down the marks. Although there might be situations that some lots of people got the same number of marks, but we, for this example's sake, we are um, we've just taken random numbers. Okay, so we have one person whose marks is 0, another person whose marks is 3. There is one person with 5 marks. There is another person with 10 marks, and so on. Ideally, this is not the way it is there in the classes. In the class, what happens is most of the people are, maximum people are on the average. Most of the people you will find, they center around a particular value. Okay. If you notice, when you draw, when you, wherever there is this population kind of game, if you plot a graph, okay, generally you will get a normal curve as in bell shaped curve. Okay, you will generally get a bell shaped curve as in, let me, something like there is only one person who got 5 marks. Okay, and there's only one person who got 15 marks, and most of them would get something like 20, 25, then another person with 26, and another person with 27 marks, and then there will be one another person with 28 marks if the exam is really hard, and maybe some person with 30 marks, another person with 30 marks, and then there might be one or two persons with really exceptional marks. Okay, most of the people would center around maybe this. So let's, how many people are there now, please? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and let's say there is one more person with, say, another person with 32 marks and another person with 30 marks. So now how many people we have in our class? Okay, and let me just draw this diagram. So B equals to, so length of B, count of B. How do you count B? Or let's say summary B. So it shows that minimum marks is 5, maximum marks is 50, and third quartile and first quartile. Okay, I'll talk about computing. How did it compute this? Okay, so now you have got these students in your class. Also, in the meantime, let's have a look at how does this diagram looks like. Zoom the plot. Yeah, this is how it's looking. Now you can see that most of the people, and this is how whenever you conduct a kind of exam, you will always get a bell-shaped curve. Okay? You will always get a bell-shaped curve. All right. Meaning, what do we mean by bell-shaped? Meaning, the outliers are lesser and average people are more. Okay, people who got maximum marks are very few. People who got really high marks are very few, and as well as people who got almost zero or very less marks are very few. So outliers are generally lesser than the people who are on the average. Okay, so this is a general behavior of people in exams, and there are many situations in the nature where you will find the histogram to be like a bell-shaped curve. Okay, only in case of artificial things such as if you have to find find out the number of times a in number of times A occurs in a credit card or a particular digit occurs in credit card, it would be mostly equal. All the digits would occur equally. Okay. So generally, when you look at certain data, you can always figure out whether it has been fuzzed or whether it's real. Okay, by basically looking at the histogram, and in case something is doesn't look like a normal curve in case of marks, there's something wrong with it. If you see there are one person on 0, one person on 10, 5, another person on 10, and so on. That means there's something wrong, because it cannot be that the there is no average people. Okay, it should always form a bell-shaped curve. All right. Now, coming back to my IQR problem. Now, let's say this is our class. This is our class where these are the marks of our people. All right. So be with me. What is the average value of B? Let's see. What is the average value of B? 28.5 is the average marks. Average marks of person is 28.5. Now, how many people remove what are the top? Okay, so and how many students are there? Count of B. How do you count length of B? Yeah, there are 16 people. Okay, total number of students is 16. Maximum marks is 50. Average marks is this. All right. Now, who are the top? So 25% is student means 25% is students means 25% of 16 is student. How many would be there? 4 students, right? 25%. So top 4 performers. Who are top 4 performers? 1, 2, 3, and 4, right? These are the 4 people. Let's take them out, or let's just mark it here. Okay, let's just mark it here. So these are our top performers from on the right hand side. Okay, and top 4 performers, top and bottom 4 performers up to here, right? 5, 15, 25. All right. So you see this, these people are in our average people. These 8 students, IQR range here is IQR range is starting from 26 to 26 to 32. Okay. All right. This is how we compute our IQR. So you always say, where are your 25 percentile people, and you then compute the middle 25. Middle range. Okay. So the way generally I'm trying to compute here using the normal calculation. But when you plot it on the graph and you cut it exactly at 25%, there will be few people who will be it will be somewhere between 25 and 26. And that's why it shows that first quartile starts at 25.75 and the third quartile ends at 32. Okay, yeah. Makes sense to you? Anusha, was I able to explain? Yes, Anusha, was that clear? So basically,
Yes,
we
it is clear.
okay, great. All right, awesome. So basically, the way it's computed right now, we have computed in a very discrete manner. We will go further and try to see how exactly would you compute IQR in case of a continuous data. In case of continuous data, you take whatever data is given to you, you plot it on a normal curve, assuming that this is just a sample of a huge data. And then you cut the graph exactly at 25%. Okay? We will go into that also. So ideally what you will do is you will, let's say here, okay? So the way it's generally done is when you have a graph like this, so what you do in this case is, where is my, yeah, here, okay. So we generally draw a normal curve on here, okay. And from this normal curve, we cut, we cut area exactly at 25% area. Okay, and exactly this side, what does this area under this curve represent? The area under the curve represents total number of people under this range. So this area is the total number of people in this range. Okay, this area, the way if you look at this frequency histogram, it shows these many people are under this range, these many people are under this. So if you compute the area of all the bars, the area of this one is 1, 2, 7, and 5, and this is 1. Okay, so if you count even the heights, okay, if you sum up all these heights, right, sum up all these heights, that means because the horizontal line is just 1, so height 1, 2, which means total 1 plus 2 is 3, 3 plus 7, 10, plus 15, and plus 1 is 16. So the total of all the heights is equal to the total number of candidates. Similarly, if you cut the graph, you prepare this graph and cut it and say these are the people under the curve. That means this represents the total number of people between this range to this range. Similarly, total number of people between this range. So you compute the volume of area of this graph, remove 25% from the left hand side, remove 25% from the right hand side, and then you say that this is our IQR, this is our first quartile, this is our third quartile. Okay, all right, all right. So that was a quick example of our interquartile range. All right. Now coming back to our example, so we talked about something called robust statistics and non-robust, or stable statistics or non-stable. Now let's have a look at it. We have 1, 2, 3, 4, and 5 and 6. What is the average and median of these values? Median and average of both 1, 2, 3, 4, 5. And how do you compute the median? So you generally 1, 2, 3, 4, 5, 6. Right? So this is your vector, okay? let me just create a vector with this name. So this is our vector. Is the font good enough for you? I think this is better. So let's say we are saying a equals to c this. Okay, these are our values. Now the way you compute average is sum of a divided by length of a. Okay, and how much is average? 3.5. And how do you compute median? So how many numbers are there? 3 plus 3, 6, which means it's even. So we pick up the middle two. Middle two are 3 and 4. So we say 3 plus 4 and divided by 2. That is our median. So this is our median. So we have average and median both. Alright. So we have happily computed the average and the median. Now, question is, out of mean and the median, who is more robust? Robust means if there is a sudden outlier. If there is a sudden outlier, who gets impacted? Mean or the median? Okay. So even out of million numbers, and there is one outlier in the numbers, who will get more impacted? Mean or the median? So it is the mean who gets impacted. You can see that clearly here. So mean got impacted just because there was one outlier we have added. Mean got suddenly impacted, while median is not. Median still sticks to 3.5, right? How? So how many values are there now? 1, 2, 3, 4, 5, 6. So instead of 6, we have 1000, right? So but the middle two values are still 3 and 4, right? And therefore the median is 3.5 while average has got changed. So out of robust statistics, if you have to figure out which one is robust, you just try to add one outlier and see who gets impacted. All right. So when you measure the spread, there are two ways we talked about measuring the spread. One was standard deviation, other was IQR. IQR is also measurement of spread. Okay, you compute how big is your IQR, how what is the range of your IQR. Okay, so based on that you can also say that how deviant is your sample. So the delta between the two, okay, the delta between the two values here, the two middle values here, 32 minus 26, okay, this is our IQR. So you subtract the two values and you will get the 6, which is your spread. Okay, so basically when you look at certain data, you try to figure out two most important things. Well, first important thing is how who is your center? What is the centroid of your data? The second thing you look out for is how spread is your data. Okay, so how spread is your data? And that's very important. That's like identifying an object out of your full dots. Okay, so we always try to figure out where is the center of the data and where is the boundary. Okay, where is like spread, how is your data spread. Now first example, so you have median and mean, which is a measurement of center, and you have measurement of spread, which is IQR and standard deviation. While standard deviation depends on mean as well as range. Range means my data varies from this point to this point. So standard deviation and mean, they are basically, since standard deviation depends on average, okay, and therefore standard deviation is very much very much dependent on the individual values, and hence in case there is one outlier or two outliers, suddenly standard deviation will be impacted really bad, similar to the average values. While median and IQR depends upon percentile number of values, as in 50% left, 50% right. So we remove all both of them and keep the central one. Therefore, most of the outliers will be removed either from the left hand side or the right hand side, and therefore the IQR would not be impacted by few outliers. Okay, because in case of IQR measurement, we actually remove the outliers from both the sides, right? And therefore, the median and IQR are robust statistics, while mean and standard deviation are not robust. All right. So while on one side you have while you on one side mean tries to be symmetric, it doesn't. It gives equal value to all the numbers. While in case of median, if you see the psyche of median is like very populist behavior. It keeps in mind total number of maximum number of values together. Instead, mean is sort of symmetric. Okay. All right. Now, sometimes when you're plotting the graph and you are finding the data totally useless, okay, sometimes you take a look at the data and you find it, okay, it's neither normal, we are not able to figure out the spread, we are not able to figure out the whether it's a normal curve or not, and when you plot it, you're not able to see a relation. In those cases, you apply transformations. Sometimes it happens that you're not able to even plot the graph. The data is so big. For example, if you try to plot the number of users, how they vary, uh, so you will find that the data is very heavily skewed. Okay, and in those cases, the transformations are very important. Transformations are very, very important. Okay, so the one reason behind transformation is you may want to see the data differently, reduce skewness, and assist in modeling and straightening a non-linear relationship in a scatter plot. Okay, so I'll show you a couple of examples, and you will see that it's quite interesting how the data looks like. Okay, so sometimes when you try to plot the data, it's totally you will find the data looks very strange. For example, here, and income per person is one such example where the skewness is really high. Okay, so let's take a case of there are so many people whose income is near zero, while there are very few people. Okay, so there are so many people whose income is at zero, while there are some people whose income is really, really higher. Okay, so when you try to plot this data on the graph, the data may not fit on the single graph. You can see that this data is looking so small that you can't even see it. Okay, you can't even imagine that is it 0 or is it zero point 0.5 or what is it. In those cases, what you do is you compute the logarithm of the values, and then the data becomes suddenly more visible. You compute the logarithm of the values, and then you have a nice graph which is actually more normal than the previous one. Okay, so there are many such cases where you will find that your data is not looking good, and sudden if you observe that your data is varying really high, for some values the data is 100 times than the other values, and in for some values the data is just 1,000 times or 10,000 times. In those cases, it doesn't make sense to try to plot it just like that. You try to take the logarithm and then try to plot the graph in on the logarithmic scale. All right. Similarly, you see this here. The graph we are showing you the life expectancy years, okay, versus income per person. Okay, here the data doesn't look good, but if you do the logarithm, the data looks like a linear graph here. You see, it's a linear kind of a graph. You can do the linear graph here. All right, and you see this one here. Sometimes there are other transformations which can be quite useful to you, such as square root and inverse. Okay. All right. So let's talk about it after a break. Hi, so should we start? Yeah. All right. So I guess Anusha and Sahab are not yet there. All right. So Sahab is there. Okay. Sahab, are you able to see the chat? Okay. So that will be easier if you use the chat because right now I have to take care of two windows. All right. Okay. So Anusha, are you back? Should we start?
Yes.
Okay. Great. Great. So here we go. All right. So we're talking about inverse and square root. There are many kind of transformations that are possible. Okay, and the way you do a transformation is very simple. Let's say we are given a like this, or what was the last data set, like this one, right? We were given b, which was like this. Let's say we want to transform it into let's say we want to subtract average of b. What was the average of b? Average of b, or average mean of b, I think. Yeah. Yeah, mean of B was 28.5. Let's say from B, we want to subtract the mean of it. So this is how it'll look. Okay, so let's try to plot B. Does it work that way? Yeah. Now you can see that if you subtract it, the diagram looks interesting. Okay. Or if you want to square B, we have this B, and we want to square it. Then how does it look? We can say b equals to b into b. Now we'll have this value, and then we can say hist of b, and it'll look like more. Now this looks zoomed, right? It become 8, and rest is smaller. So therefore we can try to do a transformation, and languages like R has been created with the mindset of doing the transformation. So we could always say things like log of b, and we'll have values suddenly of this sort. Okay, so you can say we could even produce the histogram out of our out of the logarithm which we have prepared. Good. All right. So we can easily do the transformation. Any data set, we can simply apply the transformation by saying sqrt of b. See, it has computed the square root of b, and we can, let's say we say c equals to square root of c is another vector now. We can further square root it, and we have this, and then we can plot it. Okay, so whatever operations we have, whatever operation we define for a single value, they can be applied to the full vector. Okay, so in R, whatever operations are there, they can all be applied on a vector, and those operations basically apply on each values mostly. All right, so these were the continuous graphs we talked about, the numerical ones, numerical variables we talked about, where the values are numbers. Sometimes our values are categorical, as in we have categories of values. Okay, so to explore the categories of values, we might want to utilize some other data. Like for example, here, very, not at all, not sure, somewhat, and so on. So this data you see on the left hand side. It's from a particular study where people were asked how good are they with saving money. So there were some people who said they are having very much difficulty in saving money. There are 231 people, 46% people. They have somewhat difficulty in saving money. There are 196 people and 39% such people. Then they were not very, not at all, not sure. There were all kinds of categories, right? Now, these categories are, if you have to plot a graph like this and try to analyze such kind of data or represent such kind of data, then you could either use a frequency table approach or you could do a bar plot. Bar plot is very much like a histogram where for each of the categories are on the x-axis. On y-axis are counts of the people or counts of entities in that particular category. Okay, just like in histogram, on x-axis we had range from this to this, from this to this, and so on, right? We had this, what do you call the bin? We call it bin width. Okay, so in case of histogram, we created bin width, and we did the counting in that width. Here we have already predefined categories. We can do the count of that. So bar plot is more like a histogram. Okay, all right, all right. So bar plots are for categorical variables and histogram is for numerical variables. X-axis on histogram is number line and the ordering of the bar is not interchangeable. Here, here we have to have 50 before 60, before 70, and before 80, right? So we cannot change like 60, then 50, then 70, then 80. Although we could do things like 80, then 70, then 60, then 50. But in case of histogram, these values are not something like we can switch. But in case of categorical variable, we can change the ordering of the value. It doesn't matter where somewhat or not very is there or not. Okay. So generally, if the categorical variables are not ordered, if they are not ordinal, then you can switch their value, switch their places. It doesn't matter where. Okay. Also, all right. So while doing the pie chart, for histogram for continuous variables, it's not a great idea. Okay, it's not a great idea to display the pie chart, to use the pie chart for it. While for very not for the categorical variable, we can do the pie chart. All right. Now there is something called relative frequencies. Okay, relative frequencies. Yeah. So we compute the relative frequencies from on against various kinds of variables. So here this is basically two-dimensional graph. There is on here we have a two-dimensional table. Here what exactly does it say? The question which was asked to many people are two questions. One first question was how much difficulty do they have in saving money? So some replied very, some replied somewhat, some replied not very, some replied not at all, and some replied not sure. Second question that was asked to them is, what is their income level? Is it less than 40K, between 40 to 80K? And second one was greater than 80K. Third option was greater than 80K. Fourth option was they refused. So people give these answers, the answers to these questions. Now, now we are trying to do a kind of analysis of their answers. So we have put in their numbers here. Okay, so those people whose salary is less than 40K and they are having highest amount of difficulty in saving. Okay, so there were 128 people in the income group less than 40K. They have really high difficult time in saving. Okay, and while the other income group, which has the second highest time difficulty in saving, somewhat difficulty in saving is the income group between 40 to 80K. And okay, so you can see that out of the group where the salary was between 40 to 80K, there were 63 people who said they are having very much difficulty in saving, right? Out of, or you can say, yeah. Now similarly for this group, so that's what it is. Okay, now you want to find out their how how is their relative, how are they relative to the income group. Okay, so for example 128 divided by 202, as in total number of people in that income group. So 63% people in this income group find it very difficult to save the money. 63 people, while only 43% people in this group find it difficult to save money. Very difficult to save money. Okay. And in case of people who are in little higher salary group, there are only 25% people who who have difficulty in saving money. While those people who refuse to tell their income, there are 35% people who are finding difficulty in saving money. Okay, so you can see that this is a relative way of computing things. Okay, relative way of expressing that in this particular strata, how many percentage of people are finding it difficult. Okay, so when we are computing in the same income group, we can say that in this particular income group, 63% of the people are finding in this particular income group, in this particular group, there are 100, there are 63% people, and in this particular group, there are 43%. So don't get confused between this 63 and the actual number 63. 128 by 202 is actually 63. Okay, and here it's 43%. This is 25%, and this is 35%. Okay, so this way you can compute the relative frequencies, relative values for the frequencies. So this basically helps you comparing against different income groups. Okay, all right. So these are called relative frequencies. All right. So sometimes when you have two categorical variables and you are trying to compare one category against each another, you can use relative frequencies by basically normalizing the values against a particular category. Now, this is pretty common for all. Okay, so just like bar plot or histogram, this is also very frequently used for representing data. And try to do these kind of bar plots instead of displaying the table. Okay, and these segmented bar plots help us compare the values inside a particular category as well. So here there are two category variables. Okay, two categorical variables. One is the income strata. Second is the difficulty in saving money. There are two variables which we are trying to display properly. Okay. Now here it's not relative. It's in absolute. Okay. Otherwise, the heights of all the graphs could have been equal. All right. So this is if you see here, it shows you clearly that under 40% income group, these many people are finding it difficult to very difficult to save, then somewhat difficult to save, and not very, and so on. Okay. All right. If you do the relative, as in if you average out, if you divide it, do a relative frequency, the heights of the bar plots will be same because it's one. Or you can say 100. Out of 100, 63% here, 43% here. So that way we have done the average. Okay. So, all right. So then there is something called mosaic plot. Mosaic plot is very similar to our bar. Okay. Now, if you want to remove the impact of outliers, we will use another measurement of the boundary and the center, spread in the center, which is called side by side plots, which is boxes basically. We are going to use boxes. Okay. So here the data is different. The data which we are trying to project is different. So in first year there is I forgot what was the data. So yeah, but basically we can also in the same way whatever we have done here, we could also do the okay. So we could also represent all of this data in box plots. Okay, for one strata, second strata, third strata, and so forth. So and sometimes you want to go a little fancy and you may want to use D3JS. D3JS is a library of graph where D3JS, the full form is data driven dynamic graphs. I think that's the definition. So you can have a look at this gallery. So there are lots of interesting graphs that have come up. Although the although it provides you a good library to represent our usual data in terms of the box plots or bar or whatever. The only difference with these D3JS library is it gives you the ability to present graph in very beautiful way. You can see that. So these are the untraditional new generation of graphs. Okay, and stacked bar we have already discussed, and sometimes we want to display the data in the form of tree map. Tree map as in parent-child relationship between the various sections of the data. Okay, so here you can see that the same color means same parent, and then there are children's. Okay, so we could represent a full tree as a tree map graph, and sometimes we can represent the parent-child relationship in a radial manner. You can see this is our parent, and there are the children's, and then they have the children. Okay, so there are many more innovative way of representing the same data, and these are the new generation of graph. So be aware that when you are presenting the graph to your target audience, you should know that it takes the target audience to some time to adjust to your graph. Therefore, if your target audience is not somebody who you can train, avoid showing them new kind of graphs. Okay, if because there's a amount of time which an audience will take to understand your graph, so do not assume that your audience will be ready to accept D3JS. More often what happens is when you come up with a new way of presenting data, you are able to present, that's not an issue, as well as you are able to impress your users. But your graph may not be that effective because user may not be able to understand what you're trying to explain through the graph. Okay, so there are many kinds of graph. You can have a look at this and try to see which one represents your data better. Okay, you can see that. Okay, so when you have to do a new, you are open to new kind of graph, you can even look at the D3JS. All right, all right. So now that was a very, the basics of analyzing data by the way of understanding the center, understanding the spread, and then understanding the data whether it's normal or not, as well as by doing the transformation we could represent the data in various forms. Okay, by plotting the histogram, by seeing the data in various transformations. Now sometimes, as in one objective of a data driven approach is that you come up with a pattern in the input data, right? Come up with a pattern in the input data. But more often the objective is to prove or disprove a hypothesis. Okay? Okay, so you have in mind that okay, there is always an objective of data analysis. What exactly is your objective of your data analysis? Sometimes objective might be find some correlation between my data. That correlation can be done using many ways, as in plot a graph and try to predict values and so on. Sometimes the objective is to prove a hypothesis or disprove it. Somebody came up with an idea saying there is a gender discrimination in the interview process. So this is a real case study, by the way. So these are a real case study. So somebody came up with an idea. Some person thought that yes, there may be a gender discrimination in case of interview process in organizations. The people would be not fair towards both the male and female genders. Okay, so somebody created a really nice experiment. The experiment was there are there were 48 male bank supervisors given the same personal file, and they were asked to judge whether the person should be promoted or not. Okay, so there were 48 male bank supervisors. They were given the same person's file and asked to judge whether the person should be promoted. All the files were exactly identical, except the gender of an applicant was changed. Okay, in some case, so out of 48 male bank supervisors, 24 people were given the same profile or the resume with the name as that of a male, and 24 people were given the name as female. Okay, it's a real case study. That's what makes it interesting. Now, what happened was 35 out of these 48 bank supervisors who were reviewing this resume said that this person should be promoted. Okay, this person should be promoted. And the amazing part was that it was the same profile given to all the people. Okay, and now question is, are females unfairly discriminated against? Let's have a look at the actual data. Okay, then you tell me, are females discriminated against the promotion in a bank? Okay, let's have a look at this data. You have one dimension is gender, and other dimension is whether they should be promoted or not promoted. So 21 people said that 21 people said that this profile should be promoted. The, when the profile has so when the profile has male on the resume, 1% said promoted, 3% said not promoted. Okay, while the profile had female and gender, 14 people said promoted, while 10 people said not promoted. Which means out of, and how many total? So there were 24 resumes with the gender marked as male and 24 resumes gender marked as female. Now you see that equal number of profiles were created. Same resume, printed 48 times. In 24 times it was male, and in 24 times the gender was marked as female. The name was removed from the resume. Okay. Now you see here is out of 24 out of 24 male uh, out of 24 resumes, 21 got promoted when the gender was male. Out of 24 resumes which had gender marked as male, 21 got promoted. While in case of female, which was 24 resumes again, only 14 got promoted. Okay, do you think there is gender discrimination against women based on this data, or there is nothing going on, everything is normal, it's just a blunder, it's just a mistake, it's just a statistical mistake? If you do the coin toss, it'll be the same kind of result. So, do you think, I'm asking all three of you, that do you think based on this data, can you reach to some conclusion? Can you say confidently that yes, women is discriminated against promotion? Okay, Mehndi says yes. What about you two? Sahib says yes. Okay. What about Anusha? Just based on this data.
Yes.
All right. All right. So yes. So, and how did we reach to this conclusion? Okay, how did we reach? And you will find a really very interesting cases. Let's imagine for a time being that the female resumes were say 10, male resumes were 90. Out of 90, some got promoted, some did not get promoted. And trust me, when you see those numbers, you will be amazed that how how we make mistake in analyzing this data. In this case, it is quite clear that females are discriminated against because percentage of males promoted were 21 out of 24. Percentage of female resume got promoted were 14 out of 24, which is drastically different. can this be a mistake? Can this be just a minor mistake of randomness? If if we start throwing coin 24 times, 24 times, okay, or if we start throwing coin 24 times, so maybe it's this much difference could occur between head and tails. Okay, let's see our little mathematical approach. We will try to prove and disprove by the way of the statistical inference. So this is called statistical inference. So it's an integral part of data analysis. When we look at the data, we not only visualize, represent, or find a pattern in it, we also try to build a hypothesis and try to prove or disprove that hypothesis. Okay, so all right, now all right, so there is always, when we try to do the data inference, we always have two sides of the coin. One side is, it's called null hypothesis. It's called null hypothesis. Null hypothesis means that nothing is going, it's just usual job. So there is not really anything going against women in this case. This is called null hypothesis. Okay, and so and then alternative hypothesis. Alternative hypothesis says no, there is something going on, and we need to figure it out. Based on this data, our data should support this particular hypothesis. Now we have to. Our objective is to prove or disprove alternative hypothesis by comparing it to the null hypothesis. Okay, so that's the whole idea about data inference. Okay, so in general it's like a case in the code. Okay, so null hypothesis says that defendant is innocent, as in there is nothing going on, it's just maybe a mistake of something. Okay, maybe you have small data, it's not big enough data. And then there is an alternative hypothesis. Alternative hypothesis says the defendant is guilty, there is something wrong, as in the coin is not fair, it is biased. So that's our alternative hypothesis. So we now what we do in these cases, one is we collect data, and if we already have data, as in our case we already have data that these many people said this, these many people said that. Okay, then based on this, after collecting, and we analyze the evidence, we analyze this data, we judge the evidence, could this data possibly happen by chance if the null hypothesis were true, yes or no. If yes, then reject. Okay, so if it says that no, it could, if it cannot happen, if there is something seriously going on, alternative hypothesis is true, therefore reject H0. H0 is null hypothesis. Or no, reject H0. Okay, so basically that's what we do. Okay, so either we accept null hypothesis, we say that there is nothing going on. Okay, and sometimes we say that there's something going on. So the burden of proof lies with alternative hypothesis. Alternative hypothesis is something which is saying, which is the hypothesis. Okay, the hypothesis is that there's something going on, some discrimination is going on. So for this hypothesis, there is a null hypothesis saying there is nothing going on. So the burden of proof lies with the hypothesis guy who says that no, there is something going on, we have to find it out. So the burden of proof lies with this guy. He collects the data, he tries to compare it with uh, the compares with the data with the situations where nothing could have been going on, and then comes up with the idea. Okay, all right. Same is the case with gender discrimination. All right. So this is a part of the, you know, the data inference. And how do we generally do? Actually, I think I have removed all of this, and we will try to prove it later. All right, I think we will try. We will try to take it up again later. Okay, when we talk about the normal distribution and these kind of distributions. Okay, we'll talk about this particular problem again, the data inference. So we'll try to do the data inference again. All right. Now, in case of data inference, we need a couple of techniques. We need to figure out, is it probabilistically correct or not? Probabilistically, as in, is this correct or not? It's like saying that every time I throw a coin, it's coming as head. Okay. If we throw it twice and we say that, oh, both the times it has come as head, what is the probability that you throw a coin twice and it lands up as head? Okay, it lands up as head. There are high chance of probability. Okay, the high chance, as in, it's a 1 out of 4 probability. There could have been only 4, right? And therefore, the point I'm trying to drive here is that proving null hypothesis and alternative hypothesis, comparing the two, is a game of statistics and probability. So we would like to deviate a bit, try to understand quickly how is probability related. Okay. So if you look at the whole game, what we are trying to do right now is we are going with, we are actually covering the entire landscape of the statistics and statistics, data inference, and then the big data. Okay, so be aware that while we are doing this, the the class may go on for longer time than what we had decided. Okay, so be aware, because don't I mean, because we are doing something which might take a bigger time. So I'm not in hurry. I can extend the class. So feel free to ask as many questions as possible. Okay, feel free to ask as many questions as possible. And that's the luxury in these new genre of courses, where you have few candidates in the class. Okay. All right. So should we continue with probability and distribution? These are a bit theoretical, but we from time to time we will talk about various ideas. Okay. So all right. Should we continue with probability and distribution, or do you have questions for me? Anusha, Mehdi, and Sahab. These are very important topics, and these are, they are the real use of data and various tools. Okay, these are the real use of data and various techniques. All right, all right, great. So let's start with probability and distribution. All right, so I'm hoping that you must have gone through probability in 12th class or earlier. So the So let's try to understand what do we mean by probability. In case you have any fear of a probability or these things, don't be afraid. It's actually pretty simple. It's simply, so Sahab's question is it possible that we can implement one case study? Yes, you can implement one case study. Let me try to come up with a data set so that which you can present and figure out whether it's a normal distribution or not. Okay, so let me note it down. I'll assign it to you. Inference will not be possible right now because we have to understand a little bit about computing the probability. Okay, and then we will talk about inference. All right, so let me try to form okay, to do today is, all right, is to do for today is give give a data set, and compute standard deviation, mean, IQR, and median, howsoever possible. Okay, howsoever possible. Median, mean, relative, and the other thing which I would like to ask you is to give me the histogram and tell me whether a diagram is modal, bimodal, normal, etc. Okay, so this exercise I'll provide to you. Right? Let me just give you some data sets which you can load using here. You can say file, here there is something called tool, import dataset from file. Okay, I'll give you that dataset. You can do that. All right. Yes. In so that was Sahib's question I was answering. Sahib's question was that will it be possible to give an exercise on inference? Afterwards, we will. That's the whole objective of these exercises is to be able to do the data inference. All right. Great, great. So good set of questions. Feel free to ask a question. Feel free to question me. That is better way to. I mean, these sessions should not be one way. They should be a discussion, and you're free to ask questions at any point. Okay, so a question from Mehndi is, can we create a Dropbox for our team? So a better idea would be, you know what? A better idea would be that we put it in HDFS. Okay, we can put it in HDFS, and in the HDFS, from HDFS, you can access using CloudX Lab. Okay, what do you say? All right. Let me also think. I think Dropbox is a very good idea. What we could have done is for each session. Okay, so today is 10th class. That's okay. All right, all right. So yes, let me just think over the Dropbox idea. All right, so let's understand what does it mean by a random process. In a random process, we know what outcome could happen, but we do not know in which particular outcome will happen. Okay? We know that when when we throw a dice, it will land with one face up. And that face might be between 1 to 6, right? Similarly, when we have a coin, when we throw it in the sky, we know that it will either be heads or tails when it lands on the ground. Okay, a coin standing is a very rare chance. So okay, so when we say a random process, let's understand a random process. Random process is where we don't know what outcome will be out of the given outcomes. Okay, we know that it would be some output amongst these values, but we do not know exactly which one will happen. If we know that what which one will happen, then the process is not random. Okay, all right. Now, probability of event A, when we say PA, is a probability of something, some event occurring. Okay, okay. The probability of event happening A between 0 to 1. Okay, what is the chance that something will happen? Is the chance, is the probability. Okay, one common, the frequentist definition interpretation of probability is probability of an outcome is the proportion of times the outcome would occur if we observe the random process an infinite number of times. This is also a nice way to understand probability. Probability is that if you keep throwing a coin infinitely, then you will get heads and tails equal number of times. Okay, so if you throw a coin 5,000 times, there are chances that head will occur 2,000 2,500 times and tail will occur 2,500 times. So that's a one way of looking at the interpretation of the probability. The other way of looking at the probability is the Bayesian interpretation. It says that it says that basically it's a subjective degree of belief. Degree of belief as in how many times will something occur. Although both the definitions match in some way, because the Bayesian interpretation is nothing but the frequentist interpretation said in a belief way. Okay, so they all agree that the probability of occurring something is equal to number of times it might occur out of the full sample space. Okay, so generally when you have more observation, the occurrence will be equal to the probability. Okay, all right, so let's continue from here onwards. uh, from tomorrow for tomorrow I'll cover a couple of good examples of probability that will actually give you a very good way to look at probability. Let me try to explain from tomorrow. All right, we'll see you at the same time from 2 hours from this point, which is right now it is 10 p.m. in India. It should be we start at 8 p.m. Okay, so right now it's 10:06. Okay, we are 6 minutes past. So you can synchronize your clock accordingly. It's 6 minutes past 10 o'clock. Okay, in India. So we start 2 hours and 6 minutes before this time. All right, tomorrow. All right, there is a confusion about the the, the timelines. All right. So okay, Mehdi, that's okay with you, and all right, Anusha. So we'll continue our discussion from this point onwards. Thank you, Hassan. All right. Thank you, Sahib. Thank you, Anusha. And see you tomorrow. All right. Bye bye.